This last video for your module 9. Okay. It will be cover shift register counter. If you still remember, in the beginning of our module 9, we already have a brief what you're going to cover in your module 9, which is basic shift register, and another one is shift register counter, and you're going to have two. For basic, you're going to have 4: CISO, SIPO, PISO, and PIPO. And for your shift register counter, you're going to have what? Johnson and ring counter, isn't it? So let's take a look into first the introduction first on the shift register counter. Okay, SR with a serial output connected back to the serial input produce your special sequences, which is special sequences. In normal counter, to provide individual digit output instead of binary or BDC output, you're going to adding a decoder. But much simpler to use a different counter structure with a simple decoder. It is a shift register. So shift register counter having two common types, which is ring counter and Johnson counter. So we're going to look into one by one on the ring counter, and after that Johnson counter. For ring counter, a type of CISO shift register, but final output feedback to the first inputs means that it's going to loop back. The ring counter use one flip-flop for each state, similar to what your knowledge before this for your basic SR in its sequence. If let's say for 10-bit ring counter, there is a unique output for each decimal bit. Okay, initially, let's say for your Q0 is equal to 1. Represent 0 of preset. The 1 is shifted round to the ring, so next Q1 equal to 1 represent as 1. Okay, this one you can try to read by yourself and try to understand, because the understanding of sentences is depend on you. Okay, what I can see after this, what I can teach after this is on the example for you to understand all of this statement. Okay, let's say you have this example of your 10-bit ring counter. Of course, you're going to have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All together 10 flip-flops, from flip-flop 0 to flip-flop 9. And similar to your Q0 until Q9. So you can see here that you have a connection back loop to the D there. Okay, n bit equal to your mod n, mean that this is the state number that you're going to have. If it is 10 bits, you're going to have 10 mod, which is 10 state. From 0, 0, let's say from 0, 0, and then 0, 1, 0, 2, 0, 3, and until 0, 0 back, loop back. So that is just example. So if you have like 4 bits, it's going to equal to 4 mod 4, 5 bit mod 5. Okay, so this will be equal to the number of n bits there. Example 10-bit ring, they are 10 flip-flop which make mode 10 counter. It will recycle after your n bits for your n clock cycle. After 10, it will be 11. At 11 clock, it's going to back cycle. Okay, this is the data input example. For example 7 here, the initial state. Determine the waveform for each of the Q output. Okay, let's say you're going to have Q0 until Q9. And initially, you're going to have MSB and LSB. So you're going to fit in with, is there any keywords here? Q01. Okay, it's didn't mention here, but it's okay. We proceed with the example here. Okay, this is the picture, similar picture at the previous slide there. Okay, when you have 10 flip-flop there, you're going to have the value of D0 until D9. You can see. So every single D, they are having their own value. Starting off your LSB, similar to your previous counter, LSB will be feeding at the D0, D1, D2, and until D9 is equal to 0 there. Then in terms of your timing diagram and also your table later on, what you're going to do is you're going to feed in the value of your D0 at this one. You can see here, this is all your positive clock. First of all, your D0 will be 1, and then D1 will be 0, D2 will be 1, the rest will be 0, 0, 0, 1, 0, 1. Okay, here it will be, you can see at the end of the cycle 10, you're going to have 1, 0, 1, and then 0, 0, 0, 0, 0, 0. So this is the final answer on your output. How about the input? It's going to follow similar thing, but you're going to feed it with your D0 right at the end. So it's going to start with your MSB. Let's say for the MSB, you're going to start with 0. This one is MSB or LSB? 0. Okay, this is 1, 0, 1. The rest will be 0, 0, 0, 0, 0, 0. So what happened for your D1, Q1, Q2, Q3 until Q9 is going to shift everything. So this one, this is the output 1. After your cycle 1, this is your cycle 1. Let's say for your cycle 1, it's going to be 0 here. And then this is your initial value. Then you're going to have your 1, 0 there. 1, after your cycle 1, you're going to have 1, right? But if you remember at these stages, see, Q1 equal to Q0 equal to 1 represent as 0, which is preset. That is the thing that I mentioned. You need to remember, you need to read carefully by yourself to understand, and then you need to look into the example. But if you read and you can understand, it's okay. But if I just read for you, it's going to be hard for you to understand. So Q0 is equal to 1 will be represented as a 0 to ensure it's to be a preset. Then after that, next, the 1 is shifted round the ring so that Q1 will be 1. Okay, so this is happened here. At the initial value, Okay, your LSB supposedly is to be 1 0, mana dia? 1 0 1 0 0 0 0. So here initially at starting is not nothing happen, but at the positive clock your Q0 will be 0. Why 0 is already mentioned there in front of your slide. And after that it's going to shift it to the right, and then for your Q1 just now at the sentences it mentioned Q1 will be 1, isn't it? So that's why it is going to be a preset. It will be a 1, and it will shift it when here it will shift it to here, and this one will be shifted to this, similar to the Q3. This one will shift it to here. This 0 will be shifted to this one, and this after that you're going to have 1 later on, because you have 1 0 0 0 0 0 0, right? Okay, you have 1 0 1. See, 1 0 1, and then 0, and then the rest it will be 0. So here will be shifted to here as the starting preset. Okay, that's why it's 0 there. It will be start at 0, and your data will be start at your Q1 there, 1 0. So it start at this point of your cycle. The cycle will be Q0 will be start at 0 to be as a preset. Q1 will start at your data feed in, and this will be 0 1. You can see it's moved here, it's moved here, it's moved here, similar to your preset value there. It's moved here, move here, until the end of the cycle. Okay, so this one you know already, 1 0 1, and then the rest will be 0, and it will be shifted after you meet your clock 0 there. After you meet your clock 0 at this side, 1 0 1, you can see it is continuous fill in. Okay, later on you can see how it's going to fit in the table. Okay, you can see here this is your initial value. Supposedly you're going to have like this, 1 0 1 0 0 0 0 for your first clock pulse. Q0 will be 0, Q1 will be 0, Q2 will be 0, Q3 will be 0, Q4 will be 0. Okay, this one is the final value. You can see here for your Q0. And then you're going to have the pulse clock 1. What is the value of your Q0 now? You can see at Q0, what will happen? It's going to move, right? So it will, in terms of table, it's slightly like confused. But if you really come to things, what is the difference between this timing diagram and the table, is very good for you, because normally we're going to focus on timing tables for your final exam, but in terms of Q&A, it's also can ask both. Okay, what is the correct timing diagram and etc. Okay, if let's say you can see it's moved and shifted until it finished. But for the table, you can see for the first one, you're going to fit all the value. And then it's going to shift to in front here. So now it will be 1 bring to here, and this will be shifted, this will be shifted, this will be shifted, and the rest will be 0 0 0. Okay, this is all 0, and until here. and this will be shifted at this, and 0 will be shifted here. For clock number 2, you're going to see this 0, it will be shifted to the Q0 now. So this will be 0, this one will be shifted to here, and will be 0, 0, 0, 1, and etc. You can see you're going to get the answer like this. All of these will be shifted here. Here will be shifted at the bottom side. This will be shifted. This will be shifted. And that's why you're going to get this final value, which is you're going to see for clock 1, Q0 will be 1 0 0 0 0 0 1 0. Let's check the table. Clock 1 1 0 1 0 0 0 0. Clock 2 0. What is your clock 2? Okay, this is your clock 1. Clock 2 will be 0 1 0 0 0 1. Clock 2 0 0 0 1 0 1 0 0 0 0. Is it similar Q2? 0 1. I also forgot 0. Okay, that is a preset. 0 1 0 0 0. Okay, you can see here, this is your Q0, Q1, Q2, Q3, Q4, Q5, Q6, Q7, 8, and 9. But you can see at your clock 1 here, it's slightly different. This is in terms of timing diagram. This is in terms of final for your table. But you can see it's moving and cycle back, ring, cycle back, ring, cycle back, ring. So you get this sequence of your timing diagram. You see? This is like your Q0. This will be your Q1, Q2 until Q9 there. And then you can refer, it is similar to this diagram. Oops. Where is it? You have 1 1, and then 0 1 0, rest will be 1 0. So you're going to have like this one there, another one here, quite similar to your table here. Lajunya dia. So you have this and this, similar, right, to your timing diagram. Just in terms of table, you can see this is the initial value for your data in. You just need to do the cycle thing, everything inside here in the table will be shifted to the right. That is in terms of ring counter. I think it is not too hard for you. You just need to know the initial value at this side, and everything will be shifted. And for the timing diagram, you need to follow, which is at the beginning, you need to have the preset value. If it is 1, it's going to be 0 there, and we will start at the Q1 to be 1. So then it will be following the result. Okay, let's move to our ring Johnson. Shift register counter for your Johnson counter. In a Johnson counter, the last complement output is feedback in as an input to the first flip-flop. Yeah, the sentence is quite similar to your ring counter, but what is the difference? Example with D flip-flop, but can be implemented with other type of flip-flop as well. Okay, here is the differentiation. You can see much more clear. Number of unique stages are 2 times. Just now for your ring counter, the stages will be following the how many bits number, but now you times 2 with your bits input. If you have 4 bits, your stages will be having 8 stages. If you have 5 bits, you're going to have 10 stages. So this is the equation that you need to remember for your Johnson counter. So Johnson counter will produce a modulus of 2n. If 4 bits, you're going to have modulus 8. 5 bit modulus 10. Example here for a 4 ring counter with 4 flip-flop, which make a M modulus 8 counter. It will recycle after 8 clock cycle for your Johnson. 4-bit Johnson counter. This is example. You can see the connection is slightly different. Rather than the ring counter, it's directly connected to here, right? And this is 5-bit Johnson counter. Still see the connection. And let's still take a look into example for 4-bit counter, Johnson counter. What will happen? So if let's say where is the input, it doesn't share the input value first. Yeah. But you can see it's going to repeat until 8. Where is it? 1, 2, 3, 4, 5, 6, 7, 8. And then after that, it's going to repeat the cycle back. Not repeating the shifting side, but all the cycle it will repeat 0, 1, 2, 3, 4, 5, 6, 7 cycle again, and then it repeat again for cycle 0 until 7 again. So it's repeat the cycle. In terms of the value there, it's depending also in terms of the input of your Johnson counter. If you have here 0, 0, 0, 0, and then the next clock is goes to 1, 0, 1, 1, 0, 0, 0. This one will be shifted to here. This will be shifted to here. This will be shifted to here, and etc. Similar also what is happening. Only that because this is 4-bit, what you need to remember, 4 times 2, it will be 8. But you can see might be in this example it didn't give you the value, that's why no input value. But assuming that it will be 1, what is the final output? What do you think final input? It will be complete 1 cycle, 1, 1, 1, 1. Okay, let's see here first. You're going to have the value of 0, 1, 1, 1, 1, and at this side it is 0, 0, 0, 0. So from the table, you can come up with your timing diagram, and timing diagram also will result to the table there. It's basically it's referred to the input data, but it is not mentioned here. Okay, I will double check in terms of the value, but let's say example these type of tables are popping up. So what you're going to do, you're going to have this 0 here will be cycle back using your Johnson counter. Normally for ring it will be 0 and bring here to be 1, but remember you're going to start at 1 later on for your Q1, isn't it? So that's why it will be 1 there. So the only difference between ring counter and also Johnson counter in terms of the stages there. 2n, and then it's going to be okay, this is a counter. Of course it's going to count 0 0 0 0 0 0 0 1 0 0 1 0 0 0 1 1 1 0 0 0 1 1 0 0 1 1 1 1, and then it's going to follow here. Zero, 4, 5. This is 5. This is 4. 1, 2, 4, 8. Okay. 8. This will be 9. Wait. 8, 12. 0, 1, 2. And here will be 8, 4, 12, 14. This one will be 15. This will be 4, 5, 6, 7. This will be 3. This will be 1. And it's going to go back to the 0, 0, 0. This is how the Johnson counter count the input. And you can see here for the ring counter, it's going to following the 0 0 0 0. It's after that it goes to 1 0 0 0, and then it goes to the next one 0 1 0 0, and then moves to here and here. So this is the one under Johnson counter. For this state diagram, you can see it more clearly rather than in terms of the table. I also confused looking at the table, but in terms of the state diagram, we're going to have 0 0 0 starting at the similar part. What will be go after this? 1 0 0 0. So you can see it's following the state diagram here. 1 0 0 0. After that, it go back to 1 1 1 0, and then 1 1 1 0, 1 1 1 1 0 1 1 1, and the rest. So you're following the sequence of your truth table. So other characteristic of your Johnson counter, always exists 2 unique bit compared to the other states. It will only require 2 input decoder to decode a state. So example here, you can see you have the input of A, B, and C, D. From here, you can decode and having the state by state there. So at this part, you have the AND gate required for the output, depending on the value. Upon of that, there will be a comparison of the counter. You're going to have ring, Johnson, and another one is binary. But throughout, this is 2 that important. Still, binary you still need to know in the basic. And there are several exercise you can try, because you have also here the multiple choice question. It's good for you to try, and this is the solution. Okay, I think only that for our module 9 altogether if we already cover. Please make sure you study carefully, study smart, be hardworking. And if you have any question, we can meet again in your next class session or in the extra classes later on. Okay, thank you for your watching. Stay safe. Bye bye.